Hi friends, in the last part we saw three different types of systems executing simple harmonic motion, namely it was the simple pendulum, the spring mass system and a cylindrical vessel oscillating in a liquid. The fourth system that we are going to look at is the particle oscillating in a tunnel made along a cord of earth. Let's say this is the earth of radius r and mass m, and we are having a cord here and this distance is d. Now let's say the particle has moved to a certain distance here, which is at a distance x from this center, and this distance from the center of the earth is radius r. Now with this radius r we are going to draw a circle, a sphere. This looks like a shell, right? So the particle here is just outside this core and just inside this shell. Now we are going to apply shell theorem. According to shell theorem, the force on an object inside a uniform spherically symmetric shell is 0 because of the shell. So due to the shell, it will not experience. So this particle here is not going to experience any force due to the shell, but it will experience force because of this core. So now since we are treating earth as a uniform sphere, we can write the density as mass, the total mass upon 4 by 3 pi total volume pi r cube is equal to, let's say, mass of the core divided by volume of the core, that is pi small r cube. This and this cancels and we can write mass of the core as capital M small r cube divided by capital R cube. Now if you apply F is equal to ma, Newton's law, so we know F is equal to minus gm, but the force is experienced only because of the core, right? Mass of core into mass, small m is the mass of the particle. Mass of the particle minus gmm upon r squared, which is the radius of the core, is equal to mass of the particle into acceleration. So I can cancel this, and here in m core I can substitute this value and I'll have minus gm r cube divided by r square into capital R cube is equal to a. Now I'll write a, okay, let it be a now, and we can cancel this, and thus we will have a is equal to minus gm upon r cube into r. If I take just one dimensional motion in only along x direction, so I'll have x double dot is equal to minus gm upon r cube into x. This is the equation of simple harmonic motion. So here we can write omega as root of gm upon r cube and time period as 2 pi by omega, so that will be 2 pi r cube upon gm. Okay, now here since we did not use any type of approximation, we can say that oscillation will be simple harmonic for small as well as large displacements. Now if this particle were on the surface of the earth, then we will have g is equal to gm upon r squared, and thus the time period will become t equals to 2 pi root of radius divided by acceleration due to gravity g. So this is the case for when the particle is on the surface of the earth. The next case, the next system is when the object is suspended from elastic rod and made to oscillate. So now this rod here is elastic. Now let capital L be the natural length of this system, natural length of the rod, and this is the initial case. So in initial case we are having some initial elongation delta L. So this is the initial case where we are having initial elongation delta L, and let the force here be the elastic force, which is F, and obviously there will be an mg downwards, and this is the mass m. Now after certain elongation of, let's say, delta L plus x, like after initial this is for initial elongation only, delta L, right? And now here we are having elongation delta L plus x. So from this there is an x extra elongation taken place, and let's call the force here F dash as the elastic force, and we can call mg downwards. So here the elongation is delta L plus x. Total elongation is delta L plus x. Now if y is the Young's modulus, then we know Young's modulus is stress upon strain. And what is stress? Stress can be written as force upon area, and area is A is the area of the cross section, and strain is written as change in length upon original length. So this I can write as FL divided by delta L into A. From this I can write F as y A into delta L divided by L. Now for case 1, where we are having only certain initial elongation, we can write F is equal to mg, and this F is just y A delta L divided by L is equal to mg. For the second case, we can write the equation of motion as net force is equal to ma. And what will be the net force? Mg downwards minus F dash upwards is equal to ma. So it will be mg. What will be F dash in this case? It will be y A upon L, but the total elongation here is delta L plus x. So this will be y A upon L into delta L plus x is equal to ma. Solve this, open this, we'll have mg minus y A delta L upon L minus y A x upon L is equal to ma. From here mg is y A delta L upon L, substitute here, this and this term will get cancelled, and we will have ma is equal to minus y A upon L into x, and then I can write this as x double dot is equal to minus y A by L m into x. This is again the equation of simple harmonic motion, where omega is going to be root of y A upon L m, and time period will be 2 pi root of L m upon y A. The last system we are going to look at is the oscillation of a piston of a cylinder containing ideal gas. Consider a vertical cylinder consisting of a freely moving piston of mass m. Let A be the area of cross section of both the piston as well as the cylinder, and this cylinder is containing ideal gas. Now at equilibrium, this case, the piston is at a height h from this bottom, and there is a downward force here which is mg, and there is an upward force here, and this force is nothing but pressure into area. Let's say the initial pressure here is P, so an area we know is A, so this F is equal to P into A. So the first case we can write the equation at equilibrium as PA is equal to mg. For the second case, when it has displaced, when the piston has displaced down through a distance x, the height becomes h minus x. So since it has come down, the downward force is obviously mg, but the gas, since the volume has decreased, the pressure has increased. Now let's say the pressure has increased by an amount dp, so the total pressure in that case will become p plus dp. Thus the force which is acting upwards is going to be p plus dp into area. Okay, so in this second case we can write the equation of motion as F net force will be equal to ma, which is mg downwards minus p plus dp into area upwards, which is equal to ma. So I can write this as mg minus pa minus dp into a is equal to ma. Here pa is equal to mg, this and this cancels, and we'll have a is equal to minus dp upon m into a. Now since Now considering that all the walls and as well as the piston, they are non-conducting, so there will not be any exchange of heat with the surrounding. Therefore we will say that the process is adiabatic process. And for adiabatic process we have PV raised to gamma is equal to constant. If we differentiate this, we can write it as P gamma V raised to gamma minus 1 dV plus dP V raised to gamma is equal to 0. From here we can find dP and then substitute dP here. So we'll have dP into V raised to gamma is equal to minus P gamma V raised to gamma minus 1 dV, and take that there, and you'll have dP is equal to minus P gamma upon V dV. I can substitute it here and this will become P gamma upon V into A by M into dV. We can find dV as dV is going to be final volume minus initial volume. Final volume is H minus X, height into area, minus initial volume is height into area. This comes out to be minus X into A. Substitute it here, we will have minus P gamma A squared upon M V into X, and this is X double dot. This is the equation of simple harmonic motion, where omega is equal to root of P gamma A squared upon mv, and time period is 2 pi by omega, that is 2 pi mv upon P gamma A squared. So these are the 6 systems that we just saw for simple harmonic motion. So friends, we will stop here, and in the next part we will look into some problems. Peace be upon you.